Hello, I would like to welcome you to this Aerospace Testing International and Testia webinar titled High-End Digital Solutions for Radiographic Inspection. I'm Ben Sampson, the editor of Aerospace Testing International, and today we are lucky to have with us two experts from Testia. I'll introduce them. First, we have here Safir Lazar, who is an engineer in physics with a master's degree in material sciences and NDT. He's worked at Testia for 3 years now as a product owner of NDT software, ultrasonic testing and radiographic testing. He is responsible for the specification, development and validation of NDT software. Hello, Safir.
Hello, everybody.
Hello. And then we have Tanji Lawrenson, who is an engineer specialized in radiography and tomography with a PhD in 3D microreology of non-Newtonian fiber suspension using fast X-ray tomography and finite element simulations at fiber scale. He is a RT level 2 FRANDTB and RT level 3 PNW. Hello, Tanji. Hi. All right, we'll hear from him in a minute. Okay, brilliant. So just a couple of things to run through first. Probably most of you know how the platform works, but if you have a question during the presentation, do place it write it in the box on the right hand. You should see on the right hand side of your screen. It won't be published, but I'll ask it at the end. And if you have any questions that we don't get to during the session, then the guys here will get back to you. Just email it across. So that's about it. So I'll hand over now to Safir, who's going to start off for us, I think.
Yeah, thank you for the presentation. So the topic today is to speak about an high-end digital solution for radiographic inspection, named NDTkit RT. So I will go further in the presentation. First, about the schedule, I will talk at first about some context in radiographic inspection. Then I will go further on the topic and speak about the main feature of the software. For the third part, I will concentrate the attention about the diagnostic assistance inside the software. And then I will let Tanguy speak about some NDTkit RT applications. So first, for the context, the main objective of industrial radiography is to locate and quantify defects that are present in some part in order to ensure product quality and integrity, as well to control material degradation to prevent component failure. So the current industrial scenario is evolving more and more toward digital formats and automation, and complex digital radiographic systems are replacing what we already know, X-ray film images, because they require shorter exposure time, reduce harmful chemistry, and increase automation. Also, new techniques such as additive manufacturing are emerging to face the geometric complexity and larger production rate of current aerospace components. All these aspects require to increase the quantity and speed of quality controls, which is challenging certified operator with the analysis and processing of large volume of radiographic data that require careful evaluation. So first, concerning the first slide, I will speak about the context and the challenges compared to solution and benefit for the NDTkit software. First, the acquisition, analysis, and diagnosis of several RT images are at industrial level takes time, causing lack of reactivity. Second point, the high work cadences can lead into operator mistakes. Then change of part, geometry, or any parameters on production line cause operation delay. All this often result in expenses and capacity loss. So how the NDTkit RT software can answer to these context and challenges? First, a single diagnostic tool for different multi-format sources to ease interoperability. So it means inside the software, you can open different file formats in the same way. Second point, custom tool creation and automated analysis process to reduce human factor intervention and save time. We'll see further in the presentation how the software can lead to save time and so save money. Third point, provide diagnostic tool compliant with composite and metallic quality requirements. The aim of this point is to answer to some aeronautical standards. So we'll see that the software translates the standard inside some features. And last point, acquires the capacity to read data during the whole life of aircraft or components. So it means during an acquisition or some inspection, you need to have the data that can be read inside your software for the whole life of the aircraft. So we'll see in the software that we have some database capabilities and we can connect the software with your database. So concerning this slide, I think I finished. I will go further. The second point is about the main feature of NDTkit RT software. So it's a Testia software platform that try to respond to this increment in NDT, especially dedicated to data analysis of radiographic testing images. It allows to post-process images, configure automatic tasks for easy defect detection, and optimize work efficiency in both industrial process and at laboratory level. This software is based on the same kernel as NDTkit UT, the dedicated software for ultrasonic testing inspection. And in Testia, thanks to this software, we extend the possibility in the NDT world. First, it was for the UT. Now we go further in RT, and we will see as a conclusion we can go to other NDT methods. So, as I mentioned during the introduction, NDTkit RT can work with multiple digital formats like JPEG, PNG, or TIFF file, and as well as the standard DICOM or DICOM-D images format used for data sharing in the field of medicine and non-destructive testing. NDTkit RT also offers the possibility to read standard databases with DICOM architecture. This means that the user can store their process shots not in a folder but in a database with a set of metadata. So NDTkit RT algorithm can recover images based on a more complex search than the file name. For instance, a search can be performed to get all images with an ID beginning with a specific number. The software presents a user-friendly environment that allows to easily identify the primary aspects of the images behind analysis. The main graphic interface includes a coordinate system to define the dimension of the part in pixels, millimeters, or inches. When moving the mouse through the image, the coordinate and the value of the point selected as well as the zoom apply appear on the bottom left area of the screen. The color palette on the top allows the user to change directly the image dynamic and brightness. And directly on the side panel, we will see after that we have some plugin tools management to have more options on this field. So then I will go further about some specific feature dedicated to radiographic inspection. First is a CNR measurement according to the STM. So inside the software, we have the possibility to directly on the side panel to directly calculate the contrast noise ratio. So we will see on this video, we have two modes, the automatic mode and the manual mode. First, for the automatic mode, we can see here on the side panel, you can switch between the two options and select the all directly on your IQI. So directly on the software, with a semi-automatic way, you can have a quick overview of your CNR inside these layouts. For the manual mode here, for some images that are not enough resolute, you can have some trouble with the automatic tool. So we let the possibility for the operator to directly select here on the side panel which IQI you need to select. So you can directly click on one and go to the all of the IQI and select it, and you will have at the end the SNR value. Then about other dedicated tool for radiographic inspection, we have the SNR, so signals noise ratio. So directly on the software, you can draw some region of interest. So it can be a square, some circle, there is no limitation on it. And automatically here you have the option to resize the shape by 50 and 50 square and directly have the value of CNR value and the noise. So this tool was developed compared to the standard because directly here they ask on some standard to have the SNR calculation inside this square. Concerning other features, so inside the software, you have some possibilities to make some scaling and measure. So this module allows you to resize the map by giving a resolution for the X and Y dimension. After this operation, the unit of the image must be in millimeter. the upper left panel of the image mentions you if you are in the millimeter field or if you are in the pixel fields. There are two ways to apply a scale on the map. First one, type in the resolution value here on the first frame. Or on the second way, you have a ruler and you can directly on the image draw a line and precise what is the size of this line. Like this, at the end, you will have all the value, all the measure directly in the millimeter field. After that, when you make some what we call scaling and some measurement, you can directly on the software in a manual way measure some crack, some angle, some polyline, and have directly a value on some screenshots. Then I will speak about the feature of the profile curve. So here on NDTkit RT, you have different options. You can click on one and directly draw a line. It can be horizontal, vertical, or custom line to display the pixels value. Between the profile and the image, you will have some synchronization, so you can move your cursor along the line and have directly the pixels value. After that, you can directly precise which profile you want. So you can have a line by default, or you can directly extend this line to have a rectangle and display the mean, median, or max or minimal value of this profile. So concerning the different histogram inside the software, when you open an image, you will have directly an overview of your histogram on the side panel, and you can directly make a windowing here thanks to the two vertical blue lines. Another way to perform this kind of calculation is to display an histogram inside a region of interest. So inside your image, you can draw some selections and display the value inside this selection. Like this, we'll have more options about the histogram and more details. So now we'll go further and speak about automatic image quality indicators. So inside the software, we have two kinds of IQI. So one and the most famous one is the duplex IQI. You can directly here on the software precise which IQI are displayed on your image. So here duplex IQI, precise the number of elements, the number of pair wires. The tolerance size is by default 20 as the standard, and precise which standard you want to perform an IQI calculation. So it can be the ASTM or the EN standard. So here, when it's done, you make these presets and you can, as I mentioned before, draw a line or a rectangle profile to display the different value. And inside the software, you have a tool to directly make a calculation for the IQI. So you will have at the end a table that summarizes all this information. So you can see here in green and in red the different value for the wire pair. So it means, for example, here you are resolute at the D8 wire pair. After that, I can speak about some specific tool named ASTM Shot Comparer. So inside the software on the side panel, you have the possibility to display directly images. So thanks to these images, you will be able to give a sanction. So it can concern the type of alloy, the pixel size, and the type of defect. Then 8 images will be here displayed compared to different degree of gravity, and you can easily load this image next to your current image and make a comparison. At the end, we have also some database capabilities. So inside the software, we can connect to a range of images and have the possibility at any moment to display some specific ID for the part. Concerning the diagnostic assistance. So here I will present some tools inside the software to make kind of defect detection, defect grouping, edge detection. So first, the detection of indication can be manually performed with a dedicated tool that allow finding, sizing, and analyzing defect or specific region. It can be performed either by choosing a scale of values which could contain the defect, by adjusting the color of the palette, or by subtracting a reference image without defects. So here we have an example of a set of defects that can be detected automatically inside the software. Then we see here a list of diagnostic assistance tools. So after defect detection, We can make a grouping of defect compared to some standard. We can also make a kind of edge detection to directly detect the edge or specific structure inside your images. And after that, we have some specific tool dedicating to drilling holes to have a better detection around holes inside the software. So concerning the defect detection, you have the complete list here. And then I will go further to some other tools. So first, I already discussed at the beginning, some selection, mask, and layout. So inside the software, directly on the image, you can display selection to have an overview about some statistic, some geometrical information. Here it's for the selection. For masks, you have the possibility to directly draw a mask here on your part that can be saved and load in the second step. Like this, you can hide or highlight some specific value of your image. Concerning the layout, it helps to add some legend for the operator inside the image. It can be an arrow to just indicate a specific area on your part, but you can also add some specific legend to indicate some defects or structural parts. We have some other tools for example, for the matching. Like this, you have the possibility to make a translation and rotation of your image compared to reference. This matching can be done manually, or it can be also done automatically. Inside the software, you will have a range of algorithms that will detect automatically some edge or some structural part on your element. And like this, the software will automatically translate and rotate your part to match your reference. Like this, it will help to save some time during some repetitive radiographic inspection. The third tool, it can be the calculator. So thanks to that, you can apply some manual calculation between the different image matrix. It can be a subtraction, some convolution between different images. There is no limitation. Another tool, it's the merging tool. For example, if you make an acquisition in 2 times, you can merge directly these 2 acquisitions on the same images inside the software. Another, I will say, tool that you can be used for each radiographic inspection is the optimization of the contrast and the brightness. So inside a specific selection, you can dynamically optimize the minimal and maximal value of your palette to have a better overview inside a specific selection. So concerning the automatic analysis and reporting, here you have some example of an automation process with an inspection report. Concerning the inspection report, it can be with a Word or an Excel files. And inside the software, all the features already present can be called on a sequencer of actions. It's what we can see here. So for example, here we can open automatically the image, display or load some specific selection, mask, layout. It can be also palettes, defect detection presets. And when it's done, you need to configure just one time all this sequence of action, and you can play it on a new acquisition. So it means at the end, you just need to make the work just one time and apply the same workflow on a new acquisition. Like this, you will just launch a batch of predefined action, and the operator just need to keep the focus on specific moment. So let's imagine you have a radiography inspection. You want to load some data, display some specific dynamic, some selection, create your report template. But at the end, the operator needs to keep his focus on the defect detection. So thanks to that, on the automation process, we can make some breaking point. So it means when you will run the automation process, the software will stop and ask to the operator to validate the defect detection. Like this, you keep the control and you have a double check between the operator and the software. Now I will speak about a customization process. So inside the software, it's possible to create and import some Python script to add specific feature thanks to an API. So it means the software is open. You can have access to this API and develop your own Python script. So I don't know if, for example, if you on your company you have a specific algorithm compared to your references, it's possible to communicate the software with your own features. Here you have some example of convolution filters, but you can add more complex stuff. For example, here you have an example of a filter that was developed by Tanguy. It's a complex filter that can be directly called inside the software. And like this, you have directly in a few seconds a better overview of your part and the indications are highlighted. So now I will make the conclusion. So we see that NDTkit RT offers a very user-friendly environment. It includes a wide set of standard functionalities that improve the evaluation and the analysis of radiographic images. In addition to that, you have the option to customize some tools, so it can be developed as an ad hoc for the user. And like this, you can optimize your process directly on the software. Thanks to NDTkit RT, I would say facing the digitalization is not a risk anymore, and it offers a powerful evaluation tool to improve operator work and efficiency. Like this, at the end, you will lead, and thanks to the software, you will have a better diagnostic assistance. So on the same place, you will have all the tools to make your radiographic inspection, to speed up your workflow, and at the end, save some time and money. So now I will let my colleague speak about some NDTkit RT applications that he made. Thank you.
Okay, Safir, I will start the sharing. Okay. Yeah, so I will talk about some application that we have in Testia Toulouse, France. But first, I will introduce our X-ray system. So it's a VisiConsult system. VisiConsult is an integrator. We have our X-ray source, which is a microfocus, reaching 225 kV, a flat panel size around an A4 paper format, and 139 picture size. So the picture size leads directly to the range of spatial resolution that we can obtain. So it's in between 22 micron to 90 micron, and give us the field of view around 36 millimeter by 43 and 144 by 174. So we can place part around 90 centimeters by 150 centimeters inside of the cabin, and we have a limitation of loading around 100 kilograms. With the systems, we can perform 2D acquisition and 3D, and I will show you some examples. Here are parts, it's additive layer manufacturing part that are in serial production, and here also on which we perform some computed tomography. So let's start with 2D inspection. So the empiric rules say that the detectability using 2D X-ray is that you are able to detect a discontinuity in the material around 2% of the thickness crossed by X-ray. Of course, there is some limitation with the maximum voltage of the source, but here with our system, we are able to detect 250 micron inside of 20 millimeters of titanium, and 200 micron inside of 10 millimeters of inconel. So it's a bit less than 2%. And the main advantage of our system is that we can program automated acquisition thanks to 4 displacement and 2 rotation axis. As example, you have the inspection of this part. It's done with X-ray film and takes approximately a day to reach 100% of coverage. And using specific order and part positioning in our system, of course, we can reduce this time to 20 minutes of acquisition with the same image quality. So it offers repeatability and increase the effectiveness with the help of a second station of analysis. About analysis now, I would like to spend some time on what our team has developed to help the inspector. So classically, when you have 16 byte images, you can obtain a large range of gray value inside of your histogram. And so you have to adjust the contrast and the brightness to see through all of the parts. But for this kind of part, it does not work anymore because with a classic contrast, what is displayed is too small to be inspected, and you have either choose to increase the contrast, or you may miss some indication. So this is why we develop the filter named Matisse, which is local contrast applied on the images, and as exposed, you will have no longer need for a contrast adjustment, or the area can be properly seen, and you can see the defect or indication everywhere on the part. From that filtration, we saw that we can properly see inside of the image, and we want to go further and detect some indication automatically. Thus, we develop a gradient based algorithm, which provides some highlight on the indication directly on the images and give you the following output. And as you can see, it worked well on titanium step wedge, on which we place some IQI and inclusion. So here is a simple example, but next example is a brace cylinder, on which you can see here, and here some lack of brace, and you have a very complex shape. So the output that the software gives is the type of defect, the size, Farad diameter, and the local CNR measurement, location, of course, and ferricity. And on that, you can directly use that output as a threshold. I mean, if your first set of results are not perfect, for example, on this part, it's on a ring image with our system. So you have some indication which are not defect, and so the operator can directly threshold the result on specific value of the output, or make a selection on the image to approve or cancel indication. And so like here, we can select, okay, this area was not containing defect, and you can also use some manual seeding point. So you click here, you click here, click here, click here, click here also. And so the algorithm provides some automatic growing and output. And so it grows inside of the defect and gives you that kind of result. So it's easier to do it by sending point than sizing every kind of defect. So as you can see, you have a lot of inclusion here. That's it for 2D inspection. Now I will talk about 3D acquisition with computed tomography. So compared to 2D acquisition, for having a 3D volume, you will have to take acquisition around 0 to 360 degrees of the part, and you will get, after reconstruction, a 3D volume of gray value. The detectability of this method depends on a lot of parameters, the part geometry, the orientation during the acquisition, the X-ray parameters, of course, and the filtration and more. And as the acquisition takes between 1 and 2 hours, we do not spend so much time to find a solution, a proper solution to acquire the part. So this is why we use a simulation tool to test the acquisition parameter. So you just introduce the CAD file inside of it, and you can also add directly some defect inside of the CAD file. And you just simulate the X-ray across the part, and it takes around 1 or 2 minutes if you go through a small scale of the part. And so you will get the constructed slice, and from that you can test measure the CNR and SNR value for a set of tension, current, filtration, integration number, and projection number. So you will test a set of acquisition parameters, and with the result of the SNR and CNR measurement, we are able to provide the proper acquisition parameter that is required for the parts. As application, in most of case, we perform data evaluation, looking for inclusion, porosity, lack of fusion, crack inside of additive layer manufacturing part. And we perform the analysis with both manual and automated solution. By manual, I mean it's an operator which goes through the entire volume slice by slice, or automated solution provided by VG Studio, and in more specific case, using MATLAB on development to answer customer requirements when the task is not so easy. As output, we deliver detailed report with indication, location, size, and 2D slices and 3D video. Another service that we can offer is a dimensional comparison with CAD files and expose some specific area which deviate the most from the 3D. And that's a classic analysis which may be pertinent when parts are printed. Oh. I'm locked here. I'm sorry. I may have a problem here with my presentation. Just a few seconds.
Okay, Tanguy, there's more slides to come.
Yeah, 3 slides to come, but I don't know why it is not working anymore.
Okay.
I will stop. Okay. Where do I start? Oh, okay. I don't know what happened. I will reload my presentation because I think PowerPoint just crashed. Sorry. Okay.
That is strange.
Yeah. I don't know how that's possible, but okay. Okay, maybe I will start again on that slice.
Okay.
Okay, that's good for you. Yeah. Okay. Yeah, so another service that we can offer is dimensional comparison to CAD files and expose the files that which deviate the most from the 3D representation. And that's a classic analysis which may be pertinent when the parts are printed. Okay. Now on composite, we can go further than indication highlights, and we can go through feature extraction. So here, as example, the porosity are highlighted in a green, sorry, and they were automatically detected. So from that extraction, we can display the volume of each porosity, the principal axis length of each porosity and its orientation according to this representation. And also we can plot the volume fraction on each way you want. Here it's a E3 axis, so it's a thickness axis. And the last service that we offer is catching failure inside of electronic devices. As example, here is an ultrasonic probe, which does not work anymore, but it was impossible to cut or open the device without potentially erase the initial cause of the failure or create a new one. So the idea was to scan the part at 20 micron voxel size and just get a look on the interfaces between the probe and the subtract. The initial idea of the failure was that there was no contact anymore. And when we look at the scan and if we go through that interfaces, we can see so the substract and the probe. And here you have some glue interfaces, and on the glue there were some internal porosity, and also you can observe some delamination between the two interfaces, and that's how we solved that problem. So it can be used also for failure analysis. And I think that's it. I've made every example that we want to show. Thank you.
Fantastic. Thank you, Tanji. Thank you, Safir.
Yeah.
A very good explanation there of digital radiography and the capabilities of your NDTkit software. I've got a few questions I'd like to ask. Is Safir still there, or have we lost him somewhere along the way?
Yeah.
There he is. He hasn't escaped. Brilliant. Okay. So I've just got a question here on the amount of time and efficiency, the amount of time that can be reduced on average, I guess. I mean, what are the benefits really, the direct benefits that your clients see? I mean, how much time is being saved?
So yeah, it depends about the number of reference and number of acquisition you made. So I think there is at first two options. For some non-complex part, you can make some stuff full automatically. So at this stage, it will lead at a lot of time reduction. And some other more complex part or some part at the end you will need a lot of operator validation. At the end, of course, it will lead at less time than the full automation process. For radiographic inspection, we not make so much measure, but for UT, for the NDTkit UT software, at the end you can, for example, make for some references more than 50% of time saving, and without make any calculation about human errors. So it's just a question of time. So it depends about your procedure, your references, and number of acquisition you made. But more you have acquisition, more at the end you will save times.
Thank you. With the 3D imaging, is there a lot of time to be saved?
You mean compared to 2D acquisition, or yeah, with 2D acquisition for the same part that I showed, or the O-ring, for example, I think it takes 22 minutes to scan it with 2D to have 100% of coverage, but with 3D we are around 2 hours of acquisition, but the results are not the same. You have the more detectability with 3D, and so it depends on what you want to see.
Yeah, sure. Okay, good stuff. Thank you,
Depends on
guys.
the
I have another question here about someone who wants to know the requirements for the hardware. Do people have to upgrade their equipment to take advantage of these features, or what are the requirements for the hardware in terms of computing power and imaging?
Safir, yeah.
In my case, for NDTkit RT, you can run on a simple laptop because all the processes you made on 2D images. Of course, if you have more RAM or more processor core, it will work faster. But in my way, when I make the validation or some post-processing, I just use my laptop that I made for reporting and all casual stuff. So on a simple laptop with like 8 GB of RAM and current processor, it will work well.
Okay. All right. Okay. I have a question here about materials. Are there any parts or materials that aren't suitable for NDTkit, or what are the kind of limitations at the moment?
Concerning the part, there is no limitation because at the end it's simple images. So if you have your acquisition in some TIFF, Daikon D, it will work at the end. So we have here in radiographic inspection. We are lucky because there are not so much file format compared to UOTI inspection. So.
Okay. Sure. All right. And there's a question here. Are there any features that you're planning that will be next that you'd like to try or like to promote?
Yeah, but one example is for the last slide concerning more complex filter, because for some parts, some dynamic, classical filter is not enough to highlight the defect before defect detection. So that's why in our roadmap, the first point was to integrate the filters that Tanguy and his team develop. Like this, you have everything on the same software and find some general parameters for all kind of images. And on the roadmap, yes, we want to extend the capabilities for the database connection, because compared to some technology or some company, they don't have the same system. So we are working to extend the database connection with our partners.
Okay, interesting. Okay, great. Okay, well, if you've submitted a question and we haven't had time to cover it, then I'm sure Sophia and Tanguy will work hard to get that answer to you. Do you have anything left to add, guys? Tanguy or Sophia? No. Okay. Good stuff.
No, just maybe some specific points more about customization. As I mentioned at the end of my presentation, the software is pretty open. So if customers have specific needs, we just need to discuss. And because in Testia here, we are specialized to develop a specific feature for the customers to integrate in a global solution. So don't hesitate to contact us if you have some specific needs, and we can discuss about how we can make connection between your needs and the NDTkit RT software.
Okay, great. It's a very flexible software.
Yeah.
Yeah. Okay. Good stuff. Well, that's a good point to end on. And I thank you again for your very good presentation. And I'd like to thank you in the audience for your attention as well, and wish you that you enjoy the rest of your day. Thank you.
Thank you. Bye. Have a nice day.
Thank you, guys. Bye-bye.